Okay, so a very good morning to all of you guys. uh, Today, as we were discussing about the subject which is the fundamentals of manufacturing processes. Okay, and in the last lecture number three, due to some reasons, actually, I was unable to take that online, but I shared the video with you, and I hope that maximum of you had gone through that. And okay, so in that video, basically, I discuss about the is in the second lecture we started at the end we started the subject topic, which is a patterns, that how these patterns and what kind of shapes that we can use, okay, as per the casting that we are making. So that we had discussed in the second lecture, and we start at the end of that second lecture we started the pattern allowances. Okay, so what are the allowances that is affiliated with the pattern? Okay, so these are the five allowances, that is a shrinkage or contraction allowances, draft or taper allowance, machining or finish allowance, distortion or camber, and the wrapping allowance. So in the second lecture only we discussed and completed the shrinkage or the contraction allowances. Okay, so in the last lecture we discussed about these remaining four. Okay, that is draft, taper, machining, distortion, and the wrapping allowance. Okay, after that, in that last video, I discussed about the what type of the molding sand that we have to take, as well as what is the property and what is the composition of that is required. So during that in the last video that we discussed that about the molding sand composition. So there are three basic things which is required for the molding sand. Okay, and maximum of you are civil engineers, so you are also molding the sand as per your whatever the reinforcement that you have to create. So and apart from these things also you are adding something more, because here we are just related with the casting, and this casting is actually not of a sand, but just to create a cavity we are just using this molding sand. Okay, so this molding sand is as a combination of basic sand, which is we can say that is a silica sand because that is naturally available. We are adding the clay binders along with that. So there are two types of the basic, these are the basic clay binders, which is like cavlonitic solution and the bentonitic solution. And if there is a need of the water content for creating a moisture, so if there is a need then we are using, otherwise there is no need. Okay, that depends on the property of the material, molding material that we are using. Okay, so and in the last we discussed about the properties that is affiliated with the molding sand, or that we have to keep in mind while selecting the molding sand. Okay, so these are the five basic properties, that is refractoriness, that is that depends on the, that should be withstands whatever the high temperature that is reaching, okay, during the molding. Permeability, that whatever the gas or air entrapment is there, so that will be these gases should not be a part of the mold cavity. Okay, otherwise it will create a casting defect. So for that we are using instruments. Okay, so to remove that, like gas vent we can say, and apart from that also there are different types of the elements or instruments are available, so that we are using. So that is the permeability, and green strain, dry strain, and the hot strain that I discussed, just like is green strength. We are saying like when it contains the molding sand contains the moisture. Moisture means it has a water. Water means we can say like a weight in position, weight in shape. Okay, or weight in content we can say. So weight means there's a water quantity is there. It means that whenever you are pouring the mold material, it will immediately, whatever the water quantity is there, moisture is there, that will be completely vanished out. Vanished means that immediately as you will pour the molten material, that molding sand will become dry. Okay, so if still means it has the weight means it is a moisture content, and immediately as it is going to become dry, because the molten material that we are using it at very high temperature. So if it is still withstand that strength, then we are calling it as a green strength. Okay, now after become dry, it should not there is a chances to become a crack in the molding sand. So if still it is resisting that molding material into the dry position, then that is the dry strength. Hot strength, that is we are filling the molten material, so it's not like that we immediately bring it out. We keep it for some time into the molding sand. So while when we are keeping this molten material into that and till the certification, this sand should not become a part of uh, the uh, the molten cavity, okay, or molten material we can say. Okay, so that is basically the hot strength, or we can say like whatever the temperature that is generated due to the molten material when we are filling, so that is the bearing that should be beared by this dry sand, so that we are calling as a hot strength. Okay, so that we discussed in the last one. In the last one, in the last there one thing which is related with this molding sand, that is a permeability number that we are going to discuss today. And then we will start our main topic, that is the gating system and its design. Okay, so guys, if you have any doubt in the last lecture, then you can ask me. I'm giving you just 1 minute, otherwise we'll start for this permeability number. Okay, so I hope that uh, there is no problem, or all of I hope that all of you are here only. Okay, so let's start with the permeability number. So permeability is related. This number is related with the permeability only. That is the property of the molding sand. So like is is we are using the taper section of the sprue. Why we are choosing the taper? Because air entrapment should be there. Or like whenever like this is a molten material that we are using to fill the mold cavity. So this molten material is at very high temperature. So whenever this material is at very high temperature, it radiates. It means radiations are there. Means unburned hydrocarbons are there. Okay, so whenever these unburned hydrocarbons are there, so they will there is a they are very dangerous to the health of the worker, especially. Okay, from that aspects we are thinking. So we have to remove it from this elements that we are using for the casting purpose. So for that we are using the gas vent. Apart from that, there is a separate devices available, like how we can remove these gases from that one. Okay, so for that we are going to measure the permeability number, and it is used to calculate the permeability number at different pressure. Okay, and the time. These are the two components that we have to keep in mind, that pressure and the different pressure and the time. For why we are using this one, for complete air to pass through, means whatever the air or whatever these gases are there, so that should be removed from the from throughout the process. Okay, throughout the molten material that we are filling. So for that we have to be considered, because that is a standard, because whatever this the test, basically this number is evaluated on the basis of a test. So this test, when we are going to conduct this test, there is a specific specimen is required. Okay, and the volume is also of means the test that we are conducting in a device, the volume of that is fixed, and accordingly we have to choose the dimensions of the specimen. So for that the standard specimen with 2000 centimeter cube volume is required. Okay, that air quantity can be filled into that. The specimen size that we have to prepare of the molding sand, that is diameter in the range of diameter is equals to 5.08 centimeter, and the height of that is also 5.08 centimeter. So that means cylinder we are making, but the cylinder height and the diameter both are equal. Okay, now what is the permeability number? That is represented by capital P, and in the subscript it is capital N. So that is a Pn, that is a permeability number, and that is presented by the V into H upon P into A into T. Okay, so this is the standard formula for the permeability number. Okay, so now here is the volume of the air that is passed through, the volume of air that is passed through. Okay, so that is we are considering, that is 2000 centimeter cube or cc, sorry, centimeter cube. Okay, now this is h is basically the height here, height of the specimen that we are choosing. So that is 5.08 centimeter. Okay, height of the specimen. P is basically the air pressure that we are maintaining, air pressure. Okay, that is in gram per centimeter square. Okay, A is basically the cross sectional area. This is a cross sectional area. Okay, that is in centimeter square. And if we talk about the diameter cylinder, okay, this is a cylinder, the specimen that we are using. Then this is height and this is diameter. So from this side, this is the cross sectional area. Okay, so this cross sectional area will be equals to pi by 4 into d square. Okay, so whatever the diameter is given to you, just go for it and just square it. Okay, then t is basically the time. Okay, time to pass through the air from the experiment, during the experiment. Okay, and that is always be calculated in the minute. Okay, so if in the given in the second, then we just convert into the minutes only. Okay, now here is v is basically the volume and h is the height. V is the volume, h is the height, volume of the air that is passed through from the specimen, the specimen that we are using. Okay, h is the height of the specimen, p is the air pressure that we are using into that container, a is basically the cross sectional area of the specimen that we are considering because load we are applying in this direction. So this is the cross sectional area. T is basically the time to pass through the air. Okay. Now here the is for the like specimen dimension is given to you, the volume for the air that is required, that is given to you. So if you will, this v value is given to you, that is 2000, h is given to you, that is 5.08, and this a is the cross sectional area, so that is pi by 4 d square. So from here you can calculate the value of area, that is 5.08 whole square. Okay, so from here you can get the value of a, that is in centimeter square. So from here pn will be equals to, just put the value of 2000, that is v, 5.08 upon p into a, that is the cross sectional area, that is whatever the value that you will get. For an example, x value you are getting, so this is the x, and into t. So overall, if you will take if you will go for a calculation by of these values that is given to you, so when you will calculate it, this pn permeability number will be equals to 501.28 upon p into t. Okay, so this is a permeability number. Okay, now as I mentioned in the beginning, that to calculate the permeability number at different pressure and the time, so this permeability number is depend on the pressure and the time only, that how much air pressure we are using and how much time is required for this to remove all the gases from that. Okay, so this is the basic formula for that. Okay, pn. So let's go for a numerical problem for this one, so that whatever the formula that we have gone through, so that will be clear to you guys. So calculate the permeability number. For this guy, your I need your attention and I need the answers from you guys. Okay, then only I will proceed. So just be ready with your calculators. So calculate the permeability number of a sand. Okay, that is pn we have to calculate, and that is we have seen that is 501.28 upon p into t. Okay, so if it is takes 1 minute 25 seconds to pass 2000 centimeter cube of air at a pressure of 5 gram per centimeter square. So here the volume that is given to you, so volume, the last formula that we calculated, that is 501, that is based on 2000 centimeter cube only of air that is passed through. So here the pressure is given to you, that is 5 gram per centimeter square. Okay, and the time is given to you, that is 1 minute and 25 seconds. Okay guys, so tell me the value of pn from here. Okay, uh Roman 1.179. Okay, let's see. I'm just waiting, Roman, for other values as well. At least one more answer I need, so that should we take the time in minutes or second, right, Musharraf? That's a very good question. Because last time, as I in the last slide, I told you that this time should be in minute only. Okay, and if you will see here, this time is given to you in 1 minute and 60 seconds. So what you have to do, you have to convert that into the minutes. Okay, so here 1 minute, and if you will convert this 25 seconds into the minute, so this will be like 25 by 60 minutes. Okay, so this is like plus, you can say 1 minute plus something like that. Okay, so just calculate the time from here and then put the value of it. So please first tell me the value of time from here, that how much minutes you are getting, you are getting. uh, of permeability. Okay, time, guys, you are that is 1.416 minutes. Very good, Musharraf. Okay, Roman, that's it means that that is correct. Whatever the value that you are getting, both Roman and Musharraf. So now, can you tell me the value of permeability number? Roman has already mentioned that is 70.76. Anybody else, guys? 70.80. Okay, let's see. That is 501.23. Upon pressure is directly given to you, so that is 5, and this T is like 1.416. So I think you will get it. I hope that both of you are getting the same. So I'm not going for a cross check. Okay, or should I go for a cross check? If anybody else apart from these two guys can answer me. Yeah, X, right. It's what I'm getting is that is 70.79. Okay, so this is the value that I'm getting. Both are correct. Okay, Roman and Musharraf, both are correct. I hope, guys, you both are only seriously attending these classes. Rest are sleeping, or maybe they have just turned on their Zoom class and they have kept mobile somewhere. So, okay, I will test it in between. So, okay, guys, so this is the permeability number. Okay, so next we are moving to the main topic of our today's class, that is gating system. Okay, so gating system is nothing but as we discussed in the uh, casting terminology. Okay, we discussed in the casting terminology that there are like pouring basin is there. Okay, from when we are pouring the material from the ladle, there's a first of all that is coming to the pouring basin, then it is transferred to the sprue, then there is a choke area or skim bob is there. After that there is a runner. Okay, and after that there is a gate, and then it is finally passing through the carrying at the mold cavity, and then once it is completely filled, the material is coming out from the risers. So these are the elements that we have gone through, or these are the basic elements for the casting terminology. Okay, so these are only the gating system. Gating system is nothing but whatever the elements that we are using, or from we are filling the molten material and up to the molding cavity that is reaching, we are calling these elements are a gating system, is gating elements. Okay, we can say. So just take a look into what the point that I have written. So molten material is poured into the pouring basin, then it flow through the gating system. Okay, so here the sprue, runner, and the gate, because mainly the design is based on these three only. Okay, that is a sprue, runner, and the gate. Apart from this, also like sprue and the gate is important. Not runner is not that much, because runner is just a horizontal passage through which the molten material is reaching from the exit of this sprue to the gate. Okay, into a mold cavity. Designing the gating element so that casting yield will be maximum. Yeah, guys, whenever like we are designing these gating elements, so this is a very important point, that the casting yield should be maximum. Okay, then what is the meaning of this casting yield is, for that there is a formula, that is casting yield will be, sorry, yield will be equals to the volume of casting, that is here we can say that is a VC, okay, or volume of mold also we can say, then volume of casting VC plus volume of getting elements, that is VGE. GE means getting elements, okay. So this is the formula for the casting yield, okay. Now if I'm talking about the casting yield, that it should be maximum. So here if you will see the volume of the casting, so if you will increase this one, if we will increase the value of this casting or mold cavity we can say, so here this value will also be increases, okay. So there will be nothing change, or if there will be a changes in the casting yield, then it is also very minimum, okay. Means the percentage ratio if you will change, then it will be minimum. So what is other element is present, other component is present, that is apart from this volume of the casting, other component is volume of the getting elements. So if you will like this is in the denominator, okay, this is the total. If you will see, this is the VC upon VC plus VGE. Okay, this is the casting yield. Okay, this is CY. So if you will increase this volume, okay, this if you will increase this volume, then this complete component will be increases. Okay, if this will be increases, then that will become going to be down. Means it is decreases. Okay, that will become minimum. So for that, what we have to do, we have to decrease the value of whatever the volume of the whatever the getting elements that we are using, the volume of that we have to reduce, so that the casting yield should become maximum, okay. So what, during the design, what we have to consider, we have to consider that whatever the elements that we are designing, the volume of that should be as minimum as possible, okay. We do not have to waste the size and the material also, okay, because this is the casting yield. So if you will see the casting yield, then volume of the casting means how much amount of the volume that we are filling into the mold cavity, okay, that is only the casting yield, the volume of the casting, okay. And that is the volume of the casting plus volume of the getting element. So if it will be as less as possible, then it will try to become a we can say like 100%, okay, this casting yield, okay guys. So that we have to consider in mind. So let's go to so again there are some basic principles that we have to be keep in mind before going to the designing of the getting elements, because whatever the calculation that we are going for, like for the sprue and for the getting elements gate we can say, we have to be consider these principle, we have to keep in mind that one, okay. And once again here these are just a basic principle, and I'm not going into that much detail because as I already mentioned in the beginning, that I will just brief you with the things which is very important for you guys, okay. So here I'm just keeping this just to brief you guys. So there are two basic principles. First basic principle, that is a Bernoulli's theorem. Now here most of the students are from civil engineering, so they are aware about the Bernoulli's theorem, and they had gone through this Bernoulli's theorem during the in the fluid mechanics, okay. Because we mechanical engineers has also gone derived this relationship into the fluid mechanics, okay. So this is Bernoulli's theorem. So first let's consider the Bernoulli's theorem. So here Bernoulli's theorem is Bernoulli's theorem. Okay, so if we talk about this Bernoulli's theorem, then this is a completely based on the total conservation of energy. Means total energy is conserved. Okay, total energy of the fluid is conserved. Now, if we are talking about that, how many energies that is affiliated with the fluid, then here, like I'm just considering a passage like this kind of passage, and which is at some height or elevation, we can say, from the datum level. Okay, so this is the center line. So here I am considering 2 points, that is point number 1 and point number 2. Okay, let's consider point 1 only. So this is the height that we are considering. Okay, so this is the height, that is h, we can say. Whatever the pressure is there, that is pressure P, and the velocity, the fluid which is flowing at this in this direction, at this point, it has a velocity, that is V. So how many energies that is affiliated with this one? First is or in terms of head also, like we can say. So if we talk about the head, in terms of the head, then here three heads is the total energy summation is well, sorry, let me write over here. Total conservation, just give me a minute, guys. Okay, so here if you will see the total conservation of energy, that will be equals to constant. Okay, uh, okay, so now if we are talking about this point 1 where the pressure is P, velocity is V, and the height is h, then total energy conservation of the energy, that is the summation of the pressure energy. Okay, or simply I'm writing in terms of the head. So this is the pressure head plus velocity head plus elevation, or we can say potential difference. Okay, elevation, that will be equals to constant. Okay, so here or in other terms we can say this is the potential energy, this is the kinetic energy, and this is the pressure energy. Okay, in terms of the energy, if you want to define. Okay, so this is the pressure head. So if I am talking about this, the point this is the point where we have to calculate the pressure total energy, then that will be equals to, if I am talking about the pressure head, then that is will be equals to P by rho into G. Okay, I will brief you what these terminology are, don't worry. Then it will be the velocity head, that is V square by 2g. Okay, then elevation, here we are considering this elevation, that is height is h, so this is h, that will be equals to constant. Okay, now here P is basically the pressure, that is containing at this particular point. Okay, rho is basically the density of the fluid, that specific kind of fluid that we are using. G is basically the gravitational acceleration. V is the velocity, okay, at this point. Okay, h is basically the height, that elevation from a datum level, we can say. So total summation of this head, that will be equals to constant, okay, for a fluid flow. In this is the terminology of the Bernoulli's equation. By the way, this is not directly that we are getting, somewhere there is a Euler's equations and many assumptions we are considering, after that only we are deriving this equation. But here only this equation is important, so I'm not going for a complete derivation. Okay, guys, so that's why I'm just briefing you that this is the total energy conservation. And in case of the Bernoulli's equation, or in case of fluid mechanics, this total energy of conservation of the energy is equals to constant, and that is the total energy conservation is the summation of three energy: pressure energy, kinetic energy, and the potential energy. Okay, so we can convert that into the in terms of the head as well, because in the fluid mechanics head is important. Okay, so we converted that, that is the pressure head, the the velocity head, and the elevation, that will be equals to constant. Now here if we are applying this equation, now it means if it is a constant, that it means that total energy of the total conservation of the energy, that can be means energy, like neither it can be created nor be it can be destroyed, so it just can be converted from one form to other form. But here the form is same only. So it means that like if this is the total energy at this point 1, then the total and this total energy of the fluid will be constant throughout the flow. Okay, it means that if I am considering any other point, which is a point number 2, the total energy of this fluid will be same there as well. Okay, now this is for this also we are considering that it should be a ideal flow. Okay, it should be a ideal flow. So if it is an ideal flow, then total energy at this point 1, that will be equals to total energy at the point 2. So if I am taking point 1, that I am taking subscript 1, and for the point 2 I am taking subscript 2. So this will be equals to P1 by rho into G, because rho is the density, so fluid is not changing from one position to two position, fluid is same. So I'm not changing that one. The velocity is changing because the cross sectional area here will be different, here it will be different. So this is a V1 square by 2G plus H1. If you are considering this one from the datum, this is the datum level, so this is the height H1, here the pressure P1 and the velocity V1, here the pressure P2, velocity V2, and the height, this height will become uh, more than H1, so this is H2. Okay, so this is H1, that will be equals to P2 by rho G plus V2 square by 2G plus H2. So this will be the total energy conservation at point 1 and point 2. If in case we are considering it is a real flow, if it is a real flow, guys, okay, then it should not be like this. Real flow means when the fluid is flowing in this direction, there will be a loss due to the friction, because whatever the fluid that is moving in this direction, that will be come in contact with this surface, and this surface is not like these two surfaces only, because that is a cylindrical, okay, taper cylinder. So fluid is moving into that along with the boundaries as well. So if it is moving along with the boundaries, then definitely there will be a loss. Okay, means they will try the resist, that will be resistance is will be created by these boundaries. Okay, so if this resistance is created, it means that there will be a loss of the energy. So if this will be a loss of energy, guys, just give me 1 minute, there will be some disturbance. Sorry for this inconvenience. uh, uh, Arshad, uh, yeah, tell me your question, you're raising hand your hand.
Good morning, sir.
Yeah, good morning, Arshad.
Sir, let us suppose we are installing a small wind turbine on the top portion of the car. Can we apply this Bernoulli's theorem?
Arshad, please, actually, this question is not clear to me. Means, you're not properly audible. Please, can you speak again?
Yes, sir. Suppose, sir, we are installing a small turbine on the top of a car. Can we apply this Bernoulli's theorem there?
Wind turbine, are you talking about?
Yes, sir. Yes, sir. On the
But
top of a car.
yeah, that you can consider. But Arshad, can you tell me that it's like we are considering the fluid flow. Now, this fluid can be air or liquid. That's not a matter. But it should be a passage is there. But if you are talking passage means like a taper section, a pipe is there, okay, or open channel can be possible. But if you are talking about the wind turbines, then wind turbines means there is just like a wind tunnel is there. Okay, wind turbine is not
Yes, sir.
exactly it's a turbine. it's a kind of fan is there. Okay, that fan is only
Yes.
rotating, right?
Yes, sir. Yes, sir.
Yeah, yeah, you can consider, but you have to consider the passage, the where you are applying exactly.
Okay, sir. For example, we have a tapering section with the help of which we are allowing the air to pass through that tapering section and strike the blade of the fan.
Yeah, that time you can consider.
How it will be helpful, sir? There we can calculate.
uh, you can calculate means if you can calculate the velocities, maybe most probably it is considered used for the velocity only. Like for an example, by the way, this is out of syllabus, but still I just want to brief you that if you are considering these 2 points for an example, if you are considering these 2 points, this is the 2 points. Okay, so if you
Yes,
are
sir.
applying this equation, so if we are simply talking about the wind tunnels, okay, then the whatever the pressure is there, that will be atmospheric pressure only, right? So
Yes, sir.
whether this is the point 1 or point 2, at both the conditions it will be a atmospheric pressure. So if it is a atmospheric pressure and the density of the air you will consider, so it means that both these value is constant, right?
Yes, sir.
Both these value is constant, and that will be eliminated. Now
Mm.
after that you have to just look at into that at what height you are considering these 2 points. Okay, means from the datum level or from the earth, means what is the elevation, total height of the wind turbine basically where you have mounted. So that height you have considered, and accordingly you can manipulate, like initially you have the wind energy uh, and the inlet, and at the exit you want to calculate the velocity of that. So that wind energy you have already calculated, these two elevations that you already have, so you can get the value of v2. So where exactly you want to take the output, that is how you can take.
If we are using, sir, tapered section, then the pressure head will be different, sir.
No, pressure rate will be same. Pressure rate will be same because the total there is another equation, that is a continuity equation that we will consider. uh,
Mm.
for that I cannot speak about that one. Okay, just I will brief you in the next one only.
Sir, if we are changing the cross section, that means the velocity will increase. When velocity increases,
No,
pressure
that
decrease.
depends, Arshad, that depends that what kind of cross sectional area you are changing. If you are varying the cross, means if you are increasing the cross sectional area, then velocity will be decreases. If you are if you are decreasing the cross sectional area, then velocity will be increases, but the total volume flow rate of the air or the fluid, that will be constant.
Yes, sir. That indirectly changes the, sir, pressure head.
No, never.
Okay, sir.
Okay.
Okay, sir.
Okay, guys. So here there is one more thing, two more thing, that is a continuity equation. So continuity equation is continuity equation is like the flow rate of the liquid for a particular system. So this is nothing but this can be considered in two ways. First is the mass continuity, that mass continuity equation in terms of the mass flow rate or in terms of the volume flow rate. Okay, so if we are talking about in terms of the mass flow rate, then that is defined by the m dot. Okay, m is the mass, and m dot is basically the mass flow rate, that is in kg per second we are considering. Okay, so that will be given as rho into g into v. Rho is the density, g is the gravitational acceleration, and v is the velocity. This is in terms of the mass continuity equation. Okay, or mass flow rate we can say. Or if we are talking about in terms of the volume flow rate, then this volume flow rate will be given as q. Okay, this q will be equals to area into velocity. So if we are talking about 8.1 or point 0.2, from if we simply are taking this one, that in 8.1 or point 0.2, if this cross section, whatever the volume of the this volume flow rate, means total volume at this cross section per unit time, when it is moving towards at the point 2, so this volume will that be like whatever the volume flow rate of 1 will be equals to 2. obviously, because this volume flow rate is not changing, because whatever the volume flow rate that is at the inlet, that will be at the outlet only. If it is varying, it means that something, there is something going on in between the device itself only. Okay, so what we are considering that, sorry, this is like this is the area into velocity, that will be equals to constant. So if you are applying this equation for the two conditions, then it will be a1 into v1, that will be equals to at into v2. Okay guys, now here in fluid mechanics generally we do not consider this equation, but when we are talking about the thermodynamics and the thermofluid, that time we can consider this equation, because the mass flow rate we are considering, that if the mass flow rate is same, so obviously, if if guys please listen, if the mass flow rate is constant, then the density of the fluid cannot be changed, it will be constant throughout. And the g is basically, that is depends on the space, so that will be constant. And that is depends on the velocity only. It means if the mass flow rate is constant, it means the velocity at the one point and the 2 point is constant. But this can only be possible when we are taking the cross section throughout, means same cross section throughout the length. Okay, so if we are taking example of this v1 and v2, in this case mass flow rate cannot be equal, because at the 1 and point 2 the velocity is different. That's why we are not considering this equation for the fluid mechanics. Okay, generally for the dynamic flow or static flow, okay, only we are considering this equation, that is q equals to that a into v. And if we are taking it for the two conditions, that is a1 v1 equals to a2 v2, means volume flow rate. Okay, there is another term, that is a Reynolds number, and maximum of the civil engineers are aware about that. This Reynolds equation, this Reynolds number is nothing but the ratio of the inertia force to the viscous force, that, but that I'm not considering here. It is just, if you will see the equation, then that will be equals to rho into v into d upon mu. uh, Civil engineering guys, can you tell me that what is this d I'm writing over here? D is dia, Roman, right, D is dia. But actually, okay, so here I'm just taking, okay, I will brief you that here rho is basically the density, v, d is dia, v is velocity, right, and viscosity. Okay, so this is rho is basically the density, v is the velocity, velocity of the fluid, mu is the viscosity. But there are two types of the viscosity: dynamic viscosity and the kinematic viscosity. So this is the dynamic viscosity, right, right. This is the dynamic viscosity. Okay, here the d is basically the diameter. But generally, if you will see the this formula in a standard book, okay, for an author's books, then it will be written like rho v into lc upon mu. This lc is basically the characteristics length. This is a characteristic length. Okay, so in case of the if we are considering the example of the pipe only, then this characteristic length will be equals to the diameter only. Characteristic length means how much cross sectional area, means what is the cross sectional area through which basically the fluid will be flow throughout. Okay, so what is the cross sectional area? Now this cross sectional area is defined by which terminology? It is defined by the diameter. So this diameter, this is the diameter, length, so that this fluid is continuously flowing in this length only. Okay, so that is the characteristic length. Okay, so exactly it's rho vd by mu. So here in case of the laminar flow, in case of the laminar flow, this rho e is less than 2000. Okay, for the pipe flow, for pipe flow. Okay, this rho e, that is sorry, Reynolds number is less than 2000 for the laminar flow. If it will be become equal to 2000, then we call it as a transient flow. And if this re is greater than 2000, then it is, we call it as a turbulent flow. Okay, but here we are not going to consider these two things. We are whatever the elements that we are assuming, whether it's a pipe or taper pipe or any but anything else, if it is a pipe flow, then we are considering that this should be less than 2000. So please keep in mind these three things. Okay, so these are the two principle, that is a Bernoulli's theorem and the continuity equation that we have to keep in mind, and the Reynolds number that we have to keep in mind. Here, Arshad, I want to give answer of one of your question that you asked. Here, as you said that pressure head can be changed. Okay, if the velocity will changes. Yeah, if right, you're right, because if we talk about these generally this equation, Bernoulli's equation, then this total term is equals to constant. Okay, this total term will be equals to constant. So if it means if you are moving towards the second points, okay, it means that velocity is decreasing. It means if this terminology is decreasing, if this terminology is decreasing, then it can, there is a possibility, because that will be equals to constant when we are moving to the second position, that whatever the total conservation of the energy, that will be equals to constant. So if this energy is decreasing, it means that either this one is increasing or this one is increasing, or both, right? So if here, as I said in the beginning, no, the pressure cannot be changed, because of this reason, that elevation is also there. But if you will talk about this example, then you can say that maybe here the pressure will not change, because the elevation only itself has giving its own role. Okay, because this h1 is lesser than h2. Okay, so elevation is increasing. But if you will take an
But
example of Arshad,
but sir,
yes,
in case of venturi meter, we are changing the cross sectional
I'm
area and hence pressure
yeah,
pressure
right.
gets
I'm taking the example of that only. Means similarly like a venturi meter, that if you will take an example like same venturi meter is like this. Okay, so if you are at the horizontal, you are considering this one. Okay, and this is like elevation. Okay, so this is the point one and this is point two, right? So these are the same condition for the elevation, means h1 and h2 will be equals to, means both are equal. So in this case, the
same.
Bernoulli equation will become v1 by rho g plus v1 square by 2g, that will be equals to p2 by rho g
Mm,
plus v2 square by rho g, sorry, 2g. So if you are
root.
this here 1 and 2, so the velocity is increasing. If this velocity head is increasing, no doubt the pressure head will be decreasing, because at that time we are considering both are constant. Is it fine, Arshad?
Yes, sir. Yes.
Okay, great. So let's um, okay. So guys, anyone of you have any doubt, you can ask me. Okay, okay, sorry. Yeah, Roman, right. I took this wrong calculation. Not wrong. It's this laminar flow, it is 2000. For transient flow it is in between 2000 to 4000, and for the turbulent flow it is above 4000. Sorry, I somewhere that my mind was in that question, that's why. Okay, so this is exactly the number for the Reynolds number for the pipe flow. Okay, guys, and it is and here if we are here, I am talking considering only for the pipe flow, because whatever the elements that we are using, whether it's a sprue, it's a runner, or whether it's a gate, all these are taper in section or hollowing, sorry, means pipe in section, means in the form of pipes only. But if you are considering for the, if you will go for a open flow, okay, open channels, then these value will be different, guys. Okay, so civil engineers are well aware about these things. That will become in terms of the lakhs. Okay, so that for that this Reynolds number, Reynolds values is different. Okay, so this these 2000, 4000, so this is value for the pipe only. Okay, okay, let's design the elements. So for pouring basin there is not that much design, but we have to be considered that whenever we are taking the pouring basin, we have, as I mentioned in the that when we are discussing about the casting element, I took this example like this, that this is a pouring basin. So exactly I told you there that exactly it is not like that. Exactly it is looks like this one. Okay, like this one. Okay, so why we are taking like this, because here we are keeping the ladles, okay, and through which the molten material is coming, and this molten material is first, it is contact, make the contact with this this boundary, and that will move along with that. Okay, now as it is moving, so it will start filling this area. Okay, it will start filling this area. Now when it will fill up to this height, okay, up to this height, and after that this material passes into the sprue. Okay, this is a taper section is the sprue. So here if we are considering that this is the inlet diameter of the sprue, which is capital D. So this curve radius will be equals to either 1.25 d, or this is 2.5 r. If you will write 2 r, then it will become 2.5 r. So in some of the books it's written that is 2.5 r. Okay, and this height would be taken as 2.5 d. Okay, so please consider this design whenever like we are designing this pouring basin. So for this there is not that much required, because we are using this pouring basin just to store the material for the time being. Okay, for the time being. So design is based on to reduce the velocity of the liquid molten material. Okay, it will store in the metal to for the sometimes only, due to which particles float over the top surface. So here why we are keeping it like this, because if there is any slag particles is there, slag is that will create a casting defect, because slag is like slag is like, we can say like, sometimes we are using the flux in which some kind of sand is exist. So that sand is, we do not want that this sand should become a part of the casting, so that will create a that will create a casting defects. Okay, so that will if there is any slag, then that will be like come to the top of this one. So after that we can just take it out, not by the hands, because it has a like, it is a molten material and it has a very high temperature. So there is a filters are available, so through these filters we can just take it out, this slag, and rest of the material is passes through the sprue. Okay, so for the sometimes, due to which the slag particles float over the surface, top of the surface, so that and also like for the smooth flow we are taking. Okay, so that if it will fill up to some specific height, then it will be easily flow, means there will be a no impact kind of loading, it will be a smooth flow. Okay, so this is the pouring basin, it is very simple. But the main design is now come to the sprue part. Okay, so let's design this sprue. So this is a guy, this is the pouring basin that I'm considering. Okay, uh, please consider like this. Okay, now here this is the sprue. Okay, so this is exactly the sprue that we are considering, but as I already told you guys, that we are not using the straight section. Why we are not using the straight section? To avoid the air aspiration effect, or we do not want that this air should become a part of the mold cavity or mold, we can say. Okay, so that will not become a part of the casting, so that's why we are adding into that. Okay, now here we are considering two things. First is the height of the pouring basin that I'm considering, that is HP. This is P in the subscript. So this is a height of the sprue, sorry, pouring basin, height of the pouring basin, and this is the height HS. That is the height of the sprue. So from here the sprue is started, and here this is the final. So this is the sprue height. Sorry, height of sprue. Okay, and this is the total height from this point to this point, so this is ht. Okay, so this is ht will be equals to hp plus hs. Please, you can also write in this terminology. Okay, so now here I'm applying the Bernoulli's equation. Okay, because I just want to design this one, so that is the sprue. Okay, so let's design it. So first I'm considering Bernoulli's equation. I'm considering this one as the datum level. Okay, this one as the datum level, and I'm applying the Bernoulli's equation at the condition 1 and the condition 2, point 1 and point 2 also you can say. So here just consider the pressure, that is P1, velocity is V1, and the height here is HP. Okay, and this is the datum level itself, so height will become 0, this H2 will be equals to 0, this H1 will be equals to HP, H2 will become 0, and here just consider the pressure, that is P2, and the velocity V2. So just apply the Bernoulli's equation. So Bernoulli's equation is what? That is P by rho g plus V square by 2g plus H equals to constant. Okay, so just apply for 1 and 2. So this will become like P1 by rho g plus V1 square by 2g plus H1. On behalf of this H1, I'm just writing this HP. Okay, this is HP. That will be equals to P2 by rho g. Okay, plus V2 square by 2g, and H2 will become 0. So this is 0. Okay, now if you will see that when we are pouring the molten material from the ladle, so here that will be a atmospheric pressure only. Okay, here this will also be the atmospheric pressure, right? Because is the molten material is coming from this side, this molten material is filled up to this, and this is coming to this side. Okay, this side, so this is the molten material is coming, so here it also be considered as a atmospheric pressure. Here is also like this molten material only, this passing through this one, so this is also the atmospheric pressure. Please keep in mind, wherever like we are considering inside the sprue, this is the atmospheric pressure only, point 1, point 2, or point 3. Okay, so if this is point 1, this is the atmospheric pressure, this is P1, and P2 will be equals to P atmosphere. This is the first condition. Second condition is, if you will see, this is the open channel. Open channel means a large cross sectional area. Okay, and if you will see this one, this becomes small, means not this much small, but little bit in comparison with this one, it becomes small. So if you will compare the velocity at V1, then this V1 velocity is very very lesser than V2. Okay, and you can say like here you are just pouring the molten material, so this velocity is very small, and this V1 is not almost equal to 0. Okay, because we are just pouring this one. So if it will become 0, then this value will be this will be cancelled out from both the side, because both are atmospheric pressure. This value will be eliminated, that will be equals to 0. In the left hand side only HP is remaining, and in the right hand side only V2 square by 2g is remaining. Okay, so from here you will get the value of V2, and that will be equals to root square 2g HP. So this is the equation number 1. Okay guys, I think you do not have any doubt. Okay, so this is the equation number 1. Let's apply this equation for this one, that condition 1 and condition 3. Okay, same equation, Bernoulli's equation for the condition 1 and condition 3. So if you will apply this equation for condition 1 and condition 3, then for the condition 1, okay, from here you are taking, now this is the datum level. Okay, so if this is the datum level, then this is the pressure P1, velocity is V1, and this height H1 will become this time HT. Okay, because this is the height of HP plus HS from this datum level. Okay, so this height will become HT. Okay, now here the pressure will become P3, which is the atmospheric pressure, but first of all we will just write it. Then the velocity is V3, and height, that is H3, and that is datum level only, so that will be equals to 0. Okay, let's apply this condition for the Bernoulli. So this is P1 by rho g. Okay, V1 square by 2g plus H1. So this H1 is equals to HT, or in terms of the HP plus HS also you can write, equals to P3 by rho g. Okay, plus V3 square by 2g plus H3. H3 will be equals to 0, because third point is at datum level only. This is at the datum level only. So again, P1 and P3 is the atmospheric pressure, so these term will be eliminated. Here we consider that this velocity is very lesser than the V2, so here this cross sectional area is decreased, so the velocity has increased. So here also like you can consider the same thing, that is V1 will be very very lesser than V3, and V1 is almost equal to 0. So if you will consider this one as a 0, then this will be eliminated. In the left hand side only HT is remaining, and in the right hand side this will be V3 square by 2g. Okay, and from here you will get the value of v3, that will be equals to root square 2g into ht. Now here this is the equation number 2. Now here you can ask me one question, that why we are calculating this velocity. Okay, there, what is the meaning of that? What is the meaning of calculating this velocity? There is no meaning. Okay, till now there is no meaning, we are just designing the sprue, so how, why we are keeping this one? So here uh, why we are calculating this one, because if you, first of all, what we have exactly have to do is we have to go through what is the actual volume flow rate. So what is the volume flow rate? That will be equals to q, and that will be equals to, if we are talking about this sprue, then this is affiliated with at this point, that is at the point number 2 and at the point number 3 at this point. So this is sprue, whatever the volume flow rate at the point 2, that will be equals to at the point 3 the volume flow rate. So if this q at 2 point, that will be equals to at the 3 point, so it means that a2 v2 will be equals to a3 v3 that will be equals to a3 v3. Now here what I'm doing is just put the value of, for this values only I'm just calculating this v2 and v3. Okay, so just put the value of v2 and v3. So this a2 into v2 is 2 ghp that we calculated, and a3 will be equals to root 2GHT, right? So if you will just take a ratio of A2 by A3, that will be equals to root square HT by HP. Okay, and that is 1 by 2. And if you will take HT by HP, that will be equals to A2 by A3 whole square. So this, can I write like this? Because just square it both the sides, so this will be eliminated, it will become 1 and it will become square. So ht by hp will be equals to a2 by a3 whole square. So if you will compare this equation, that this is a y and this is x, so this will be like y equals to mx square. If you will compare this equation, then that will be equals to y equals to mx square, where m is equals to 1. Okay, and x will be equals to the ratio of this area, y is equals to ratio of the height. So now if you will see this equation, then this is the equation of the parabola. This is the equation of parabola. So if you will see exact shape of this sprue, then it should be, means initially what we considered, that it should be a constant diameter, but that is not exactly like that. We consider that we have to take it, we have to consider that into the taper. So exactly it's not taper, but it is a parabolic in shape. This is a parabolic, this blue colored dots, if you will see. Okay, so this is a parabolic in shape, parabolic. Okay, so this is, and but actually this is ideally, it is, this is ideal. We have to consider parabolic, because from the equation what we are getting, but actually we are using this taper. Simply, why we are using the taper, there is a simple answer for that, that geometry, formation of the geometry, this parabolic geometry is not an easy task, it takes a lot of time. So that's why we are using the taper section. By the way, maximum things that whatever the actually shape that we have to consider, that should be parabolic, so that this air aspiration effect can be prevented. Okay, but we are choosing this taper section accordingly, so that uh, that should be like 90% or 99%, it should match with the parabolic shape only. Okay, so exactly it is a parabolic shape, but we are considering it for the taper section, so please keep in mind this one. Okay guys, so here if you have any doubt, you can ask me. Okay, so no doubt. Okay, uh, let's move to the next one, which is a runner. So runner design is not that much complex. Reason is a runner is just a horizontal passage, okay, through which just we are filling the molten material. So, actually it is considered to be a trapezoidal in shape. Okay, so if you will see this one, then this is the trapezoidal in shape. This is the cross section. Okay, so this is the width of that. Okay, and this width is nothing but that is the twice of the height of that, not diameter. This d is basically the height. Okay, so this is the height. So this is the d diameter. Sorry, d is the height here, and this width is equals to the maximum width is equals to two times of the that height. Okay, so this is we are considering this trapezoidal in nature. Why we are considering this trapezoidal is in nature? Because from the heat transfer point of view, from the mechanical engineering point of view, from the heat transfer view, the in the trapezoidal the in the trapezoidal the heat transfer loses like this optimal this means because this passage we are using like for an example, this is a pattern, this is a sprue. Okay, there's a this choke kind of things or a skim bob we can say, and then we are using this uh, runner. Okay, so when we are this is the gate is there. So is this runner is nothing but through which a horizontal passage in which the material is just flowing, okay, before entering into the gate. So like is the material has been not entered till now in the gate. So what we want is there will be the they should not become like they should not cool very easily. Okay, so what we want that whatever the heat that is passing through these area, that is passing through these cross sectional areas or these peripheral areas, that should not be that much large. Okay, whatever the heat is there, that should be accommodated into itself only, so that it will be hot. This cross section boundaries of this one or peripheral boundaries should be hot. Okay, so that this temperature should be retained. Whatever the molten material is at in the liquid form or some specific temperature, so that temperature should be retained. Okay, and then only we are flowing. If just consider that if it is aluminum and that is flowing at the 1000 degrees centigrade, and the cross section area of that runner you are choosing like the temperature of become 800. So the material before entering into the mold cavity only that will become start solidifying. Okay, so we have to keep that into the mind, then only that's why only we are considering the trapezoidal in shape. But again, manufacturing of the trapezoidal hollow sections is not an easy task. Solid section is an easy task, but hollow section, making hollow section in the trapezoidal is not an easy task. So for that what we are taking, we are just making the cylinder only. Okay, means hollow cylinder only we are considering. Okay, but in case if we want to still like as per the materials only we are considering these shapes. So if we are considering the high temperature alloys or high entropy alloys we are using, which is melted at very high temperature. So for that outer shape that can be made, that we can prepare by the trapezoidal. So inside what we are doing is we are making some hollow section. Now this hollow is nothing but the cylinder only. Okay, so that we are managing for that. Okay, so to minimize the heat transfer losses for easy manufacturability, circular cross section will be considered. Okay, the cross section of that considered as a circular. Okay, so this is a simple design for the runner. Let's move to the gate design. This is very important, guys. Okay, so gate is nothing but this is just the passing the molten material from the runner to the uh, mold cavity, we can say. Okay, guys, here I'm just waiting for 1 minute. Okay, so gate is just an element which is allowing the molten material from the runner to the and passing through the to the mold cavity. Okay, so that is a gate, or sometimes in the books it is written as in gate systems. Okay, and these are like four types. So this is the top gate, bottom gate, parting gate, and the step gate. Okay, So design is basically here is based on two gates only, that is a top gate and the bottom gate. And parting gate is nothing but a combination of these two only, that is a top gate and the bottom gate. Okay, strafe gate is also, like we can say, this is a kind of, it's a kind of combination of parting gates only. Parting gate, that is a one parting gate we are using, which is a combination of top gate and the bottom gate. And step gate, we can say, like a combination of uh, uh, like multiple parting gates we are using. Okay, if you will see the, when we'll see the pictures. So today I will try to finish like top gate, and in the next class we'll discuss about from the bottom gate only. Okay guys, so because it's a design, so we have to be considered time calculation is there. Okay, so top gate is okay. So this is general design I'm considering. Okay, I'm not considering exactly general design, means general elements I'm considering. Okay, so this is a kind of pouring basin. Okay, which has a height which is a HP. Guys, here the shape is when we are going for a calculation part here, exact geometry is not required, but whatever the parameters that we are taking, that is important. Okay, means pressure, height, velocity, that is important. Okay, so this is the pouring basin that is we are considering. Okay, this is the first one, that is a pouring basin. Then it's a sprue, that is a tapering section up to this one. And immediately this one, that just immediately the exit of the sprue, we are keeping the mold cavity. This is the mold cavity. Okay, so this is, like we can say, this is a this is one point, this is a second point, and this is a third point. Okay, this is the third one. Okay, this is the second and this is third one. Okay, so now means top gate means is the molten material, is the molten material releases from the sprue, it immediately passes into the mold cavity. It immediately passes into the mold cavity. Or guys, in other terms, we can also like we can use this one. Sorry. So this is up to the sprue, and after that there is a choke or a skim bob. Okay, then there's a runner is there, and this is the gate. Okay, now from top gate is we are using top gate exactly means is we are filling the bottom part of that. Okay, we are whatever the molten material or the casting we are going for, that is just below the gate, not above the gate, just below the gate, please keep in mind. Okay, so here if we are like one of the figure that we considered in the very beginning, that is in the casting terminology. So this is this kind of figures. Okay, so this is the sprue, this is the skim bob or choke we can say, because exactly the skim bob somewhere it is also available. So this is a runner and this is a gate. Okay, now this molten material first will come into here. So first it will fill this area, and then it is filled up to this, and then it will move toward this side. So if we are talking about the top gate, then this is a gate and which is used to fill only the part which is bottom of that, which is bottom of that. Okay, it means that we are talking about only this part, only this part. Okay, we I'm talking about only this part. If I am talking about the the top gate. Okay, so only we are filling this area. Okay, now if we are filling this area, then what is the meaning to use the runner on behalf of that? Okay, so there is no need, because it is just flowing the material. Why I cannot use this mold cavity over here? I can directly keep this mold cavity over here, and I this directly this metal will be flow into the mold cavity. Okay, so that will prevent that will unnecessary prevent the flow of the molten material into the runner. Okay, so that's why this figure is mentioned like this. Okay guys, so this figure is so this figure is like this. Okay, so this is the exit of the sprue. That's why we are keep considering this is the top gate, and this is from which the directly molten material is coming into the mold cavity. So this is the mold cavity, and this is the HM is the height for the mold cavity we are considering, and this is the cross sectional area. So this cross sectional area is AM we are considering. Okay, so this is the total volume will be equals to mold volume will be equals to AM. into hm. Okay, now we are considering okay, let's first read what the points is available, then we'll move to the calculation part. Okay, calculation means here we are going to calculate that how much time is required to fill the mold cavity of the volume Vm, okay, when we are using the top gate. Okay guys, so here what are the points? That is, a gate is provided on the top of the mold cavity. So this is the mold cavity and top of that. Okay, the molten metal directly enters into the mold cavity from the bottom of the sprue at the atmospheric pressure. Atmospheric pressure, I have already told you guys that these are the 3 points that we are considering. Okay, this is the 1, this is 2, and this is 3. So at all these 3 points, the pressure will be atmospheric pressure only, because it's open. Okay, it's not a closed system. The velocity of metal is very high, due to which the possibility of turbulence of the liquid metal can be possible, because it's like the same thing as I told you in the beginning, in the second lecture, I think, that it's not like the molten material that we are it's not like a water tap is there, and the you are keeping the bucket over there, bucket below to that, and that water is falling into that bucket. It's not like that. But in this, if you are taking example of top gate, then it is happening like that only. This molten material is coming through this side, and this is falling over inside this mold cavity. Okay, so this is the velocity of metal is very high, due to which the possibility of turbulence. Okay, generally preferred for the ferrous material. This I will consider in the last one. In the last means when we will discuss about the, after this step get, I will discuss these things. Okay, last term, this is preferred for the ferrous material. So we are going to calculate the time. Okay guys, so time is like okay, time is required to fill this volume, this mold cavity. Okay, so this is okay, let's discuss. So first is can we get the value of velocity over here? Okay, so this is the what is the velocity that we have already calculated at the v3 in the sprue. That is the velocity at the third point. Velocity at the third point, that is root square 2g ht, right? So this is root square 2g ht, and the same terminology we considered there as well, that is hp and hs. Okay, and this ht will be equals to hp plus hs. So okay, so this is the time required to go for a total, means to fill this volume. So this will be equals to, like volume will be equals to vm. Okay, and time, that is dt. Okay, and the volume, okay, that we are considering. Okay, let's first do not consider this one. This v3 will be equals to root square 2g ht. Guys, I'm not writing this same equation again, and one for the 1 and 3 equation. I'm not going for that. Okay, from, because we have already done that one. So this is the velocity that we know, that the velocity that we are getting. Now we just have to calculate how much time to require this mold cavity. Okay, so for this one, there is a small little calculation is there. So first of all, what we have to consider, that this is the molten material start filling this one. Okay, so first obviously it will fill the bottom part of that, right? Then because it's a liquid material, it's not a solid, so that it will make these kind of shape. Okay, it will not make like that. Okay, it will be like as it is entering into the molten material, this mold cavity, then it will first spill over here. So spill means it will cover this height, then it will cover this height, then it will cover this height, and like that. Okay, so here like hm is the maximum height that is used to fill in the mold cavity. So from 0 to hm we are going for. Okay, so from 0 to hm, so when is the material is just entered, means there is no height is filled. Okay, no height is filled, it means that from that only the time is started to fill the mold cavity, right? So at this time the time is also 0, when the height, small hm we just consider that is equal to 0, and this height when it will become complete. Okay, let's consider small h. So this small h will complete become hm, that time this t will become tp. This is the boundary condition that we are considering. Okay, so this boundary condition is used to consider only when this volume of the mold cavity is filled. Okay, this is the volume. So just if we are talking about the volume of this one, then this is the cross section area. Okay, now this height is changing only. Cross sectional area is just filling the molten material into that only. So this is am into dh, which is flowing from 0 to hm, capital hm. Okay, and here in this side we are considering that this is the time, that is sorry, dt, that is the time to fill there is a specific height is also we can consider from 0 to some hm by 2 or hm by 3, hm by 4, something like that. So for that also time can be calculated. So this is the dt time, and how much area of this cross section, because because total volume flow rate, only how much amount of the volume flow that is occurs from this gate, from the top gate, with respect to the time, that will be equals to the volume that is filled in the cavity, right? So the total volume flow rate will be equals to a3 into v3. A3 is what? A3 we can consider that is a gate area, so either you can write A3 or you can write AG, that is a gate area, or V3. Okay, this is the V3 is not the volume, but it is the velocity. Okay guys, please consider this is the velocity at the gate. So this is also from at the zero height, the time is also zero. When it will become completely filled, the time will become TP, right? So this is from 0 to TP. This is dt into A3 into root square 2GHT, that will be equals to 0 to hm equals to am into dh. Okay, now this ht height is constant, because this is the height of hp plus hs. This is the ht plus, this is the ht, hs, hp plus hs. So this is constant, this velocity is constant, this gate area is constant. So this will just keep, you can keep it outside. So when you will keep it, this will become a3 into root 2 GHT. Inside the integration, this is only integration from 0 to TP, and dt will be inside. From 0 to TP, and this will be dt will be inside, right? And here am is basically the mold cross sectional area, so that is not varying throughout. So that will be like am, and this is 0 to hm, and this is dh. So when you will integrate, this is dh, so it will become h, and this is dt, that will become t. So just take okay, I'm just taking it over here. So this is am into root square 2GHT into, this is TP minus 0. So I'm just writing TP. Okay. Then it is am into hm minus 0. So this will become hm only. Okay. So from here you can calculate the value of TP, and that will be equals to am into hm upon am. Sorry, this is not am, this is A3. Okay. This is A3 or AG, you can write, that is the gate area, into root 2 GHT. Okay, and in other terms also you can write this am into hm, that will be equals to vm, that is the volume of the mold, that is vm upon ag into root square 2 GHT. Okay, so this is the time calculation when we are considering for the top gate. So this is TP, it depends on the volume that we are filling, the volume of the mold cavity that we are filling. The ag is basically the area of the gate that through which the molten material is coming, and ht root 2g is the 2g is the constant, and ht is basically the height of the total height, that is pouring basin upon pouring basin plus sprue. So on behalf of this one you can write that is hp plus hs as well. Okay, so guys, if you have any doubt, you can ask me in this one. I'm just giving you 1 minute. Okay, guys. So if you do not have any doubts, then I'm just ending today's session. So from the bottom gate we will consider into the next. We'll start from the next lecture. Okay. So thank you so much. So if you do not
Sir,
have any doubt, then you can leave.
sir,
Yes, Arshad.
जी सर, वो जैसे उसमें एनर्जी कन्वर्जन होता है ना बर्नौलीज थ्योरम में,